Dat is wel leuk.
Dat is wel ja, maar ik heb best wel te struggelen met die opdrachten. Dus ik denk dat ik dan ook vaak vergeet om obvious dingen zeg maar te schrijven. Omdat ik heel erg hard bezig ben met de vragen te beantwoorden.
Ja, gelukkig is dit een kwantum makkelijk. Dan is het tenminste meer tijd voor toevoegen.
Nee, inderdaad. Maar ik heb ook
Ik heb er echt geen zin in.
Alright, let's get back to it.
dat doet mij iets beter.
So, alright, we are thinking about things like surfaces in 3 dimensions. We're thinking about spheres, things like that. And because we're wanting to do all kinds of physicsy stuff, we need to be able to talk about the derivatives. So we need to extend our ideas to derivatives of functions of several variables. And in order to do that, we need to obviously talk about limits and continuity. I'm not going to spend a lot of time on this. I've put together very basic chunks from the textbook, just to remind you. So when you're thinking about the limit, what is it that you're trying to do? If you're thinking about a function that does something like this, perhaps, and we're interested in what's happening at this point, what is the informal definition of the limit? Well, the informal definition says that, so the limit, I think of, is where you think the function should go, based on the information on either side of the point that you're interested in. So you don't actually look at the point that you're interested in, so we're ignoring what's happening here, but based on the information from here and over here, I think that the limit should be this. Okay, it's what would be sensible. And that's the intuitive version. The epsilon delta version formalizes that in a way that you can use for maths. But this is still how I think of it. Okay, so it's basically if you took a microscope and looked very close on this side and very close on this side, what would you decide that was? And obviously if you have a function that does something like that, well, if I look from this side, I think the function should go there, but if I look from this side, I think the function should go there. They don't meet, I don't have a single limit. Okay. And you can imagine that we would do the same sort of thing if we're thinking about surfaces. So instead now of thinking about looking on either side, we're going to look at a neighborhood around a point. But I'm not going to think about this. So we're going to think about, so I've got my surface and I want to decide what the function does at that point without looking at that point. Well, I'm going to look at it all around here and see if I can come up with a sensible solution. If I can, there's a limit. If I can't, there isn't. And you can extend the epsilon delta. Now because we're thinking of a curve, we're thinking of a surface, we're going to be using x and y to help us narrow down our search. So you end up with an epsilon delta that looks at an x and y. Okay, that's as much as I'm going to say. Okay, why do we care about limits? Because limits enable us to talk about continuity. So the whole thing behind continuity says, if my function does what I think it should do, then it's continuous. So when we talk about a limit, as we've just said, we don't look at the actual point. We don't care about that point. We just say, I think, based on this information, that my function should go there. Continuity says, well, if my function actually does do that, then my function is continuous. So if the limit, what I think my function should do, and what my function actually does are the same, then I'm continuous. And you apply exactly the same thing to a surface. So we've extended this idea to continuity, which is saying, if my function actually does what I think it should do, then it's continuous at that point. All right. End of discussion about limits and continuity. we will essentially assume that our functions are delightful and continuous unless otherwise specified. Pretty much like all of calculus that you've done so far. Okay, so now we can actually talk about rates of change, which is what we wanted to do. Rates of change, if you think back to when you started learning calculus, that was all about finding the tangent line, finding the rate of change. And that was pretty straightforward what you needed to do when you had a function of one variable because you had a graph and you wanted to find the rate of change at a point and you drew the tangent line. And that was delightful. Okay, but now let's think about surfaces. So give me a moment to switch this over. Oops, where did it go? No, come back, paraboloid. Okay, so now I'm going to take that out. Alright, let's just leave those for the moment. But if you think about using the same ideas for finding the derivative, so finding the tangent, what tangent line would we use? Because if you think about a paraboloid like this, and I've got a point here, there are infinitely many tangent lines to that paraboloid. So the situation is a little more complicated. So that's kind of what we need to deal with. You might at this point think, well, okay, we've gone from a line, a curve, where we drew a line, to a surface, and we know that kind of planes are the equivalent to lines if we go up a dimension. And if you think about it, and where we're headed is, sure, there are many, many tangent lines, but there is one tangent plane. So that's kind of where we're headed. But we're going to start by thinking about tangent lines for the moment. Okay. Alright, so now let me... Okay, so what we're going to do, and I'm going to talk it through here and then show you on the iPad, is we're going to start by saying, okay, let's specify some directions in which we look. So I need that line to go away. What we're going to do is we're going to do things like we're going to take our surface and we're going to say, okay, I'm going to hold y constant. So I'm looking at this point and I'm imagining that I'm holding my y constant. So it's like I've chopped my curve along this plane here. And now I have a curve and I can think about the tangent line on this particular plane, on that curve. And that's going to be our partial derivative with respect to x. So now I'm holding y constant and I'm just seeing if y stays the same, how does x change as I move along my surface. So that's going to be my partial derivative with respect to x. And it should be no surprise that we could do exactly the same thing, but instead we can use our y's. Have I got everything? Okay, I can't quite find, I don't know where my y curve is, but you can see, so what I'm doing here now, I'm imagining that I'm holding x fixed. So I'm just looking at how my surface changes if I hold x fixed and I move in the y direction. Okay. And I mean, there's nothing particularly special about x and y except that we are working in Euclidean coordinates, and so that's what we're doing. But you might want to do this differently if you were in spherical coordinates. So you might decide to pick other directions. But for the moment, that's what we're doing. Okay.
You can only move across one variable. You say you're keeping y constant, for example, and you're seeing the change with respect to x. But it also changes in the y direction, in the z direction, sorry, at that particular intersection.
So that's what we're looking at. We're saying hold y fixed, change x by a little bit, what happens to z? So that's giving us our tangent, but it's just, well, this one is showing y is constant. Sorry, x is constant here, we're shifting y by a little bit, what happens to z? So if you think about what's happening on this surface here, okay, so I'm starting here. If I increase y a little bit, so I move a little bit this way, while keeping x constant, so I'm staying on this green plane, what happens to my z? It goes down a bit. How much does it go? Well, if I follow this green line, that's how much down it goes.
Which is going to be the unit vector of the line that we learned in the previous.
Yeah. So well, that would be the direction, the slope. Yes, the direction vector of that line. Yeah. Right. Hopefully this comes back. Come back. Okay. How do we formalize this? So, did I remind you? I probably didn't remind you. Okay, you remember that df by dx is defined as the limit as h goes to 0 of f of x plus h minus f of x over h. Okay, that should be burned into your minds. Well, we play exactly the same game when we're trying to work with functions of two variables. Now what we do is we say, okay, if I want the derivative with respect to x, so I want the derivative with respect to the first variable. So this is notation. So this is saying take the derivative with respect to the first variable, which in this case is x. Well, in that case, I'm going to hold y constant. I'm not doing anything to y. So you'll notice in both of these terms here, my y is just sitting there. It's coming along for the ride. And I do exactly what I did down here with my x. So I do an x plus h minus f of x, and I find my limit. And you play exactly the same game if you're wanting to take the derivative with respect to the second variable, which here is y. So here I'm using f sub 2, and I'm just using a different, I'm using a k here, but it's doing the same thing. Now I hold x constant in both of those, but I do the same thing with x and y. You'll be happy to know you will not have to calculate things using this limit definition. It's just so that you can see where it comes from. Because what this tells you is that whenever you want to find the derivative of a function of two or more variables in a particular direction, so with respect to x or with respect to y, you can use everything you already know. You just pretend that the variable you're not interested in is a constant. Yay! And then you forget, and then you get sad. But that's okay. All right, so let's dive straight in and have a look at this. So I've got minus x squared minus y squared minus 4, which is in fact the parabola that I was showing you earlier. And I want to find the derivative with respect to x. How do you treat constants when you take derivatives? What happens to them? Okay, so if they're multiplying a variable, they come along for the ride, nothing happens. But if they're added, they disappear. Okay, so if we're looking at this thing, the derivative of this bunny with respect to x, so our first variable, what is the derivative of minus x squared with respect to x? Minus 2x. Okay, that's good. What is the derivative of minus y squared? 0. Okay, and minus 4? 0. Okay, so we're done. Well, that was easy. All right, what's the answer here? It should be the same thing except with... All right. Okay, so test yourselves. Please, with this function, x squared sine y, find the derivative with the partial derivative with respect to x and the partial derivative with respect to y.
Would it be more correct to just say minus y squared dx in case y can be expressed in terms of x?
No, because what we're explicitly saying is that we're keeping y constant. So this notation says y is not changing. We will deal with
even if it can be expressed with x, we don't care because
No. So this is not implicit differentiation.
Okay.
Which is kind of what you're thinking of.
Mm-hmm.
This is partial derivatives. So here we're saying explicitly y does not change, and therefore if we take the derivative it's 0. Yeah.
Is there a reason why we derive in terms of x for f1 or is that just what you chose to do the f1 first?
So f1, so the 1 is referring to whoever you put first here.
Right.
Yeah. So we will talk about other notation that you see. But let's just check this. All right, so what's my derivative of this bunny with respect to x?
2x sine y.
Okay, so I'm hearing a 2x sine y. Do we get any advance on that? Okay. Does it make you feel twitchy? Yeah, why is it making you feel twitchy? Right? Because you feel like you should, because you had to remember the chain rule so much, and now you don't. Ah. Okay, so it is a little weird. So kind of have a mental flag going here. Partial derivatives. You don't chain rule it, unless of course, and if we'd had an x in here, then you would have to chain rule it, and it would still be weird. Okay.
Yeah, what would it look like if you had like sine x plus y?
So if I had sine x plus y inside, are you thinking?
Yeah.
Okay.
I can still the x squared too.
Sorry, okay, well let's do it. Okay. How do I tackle this bunny? Right, it's going to be a product rule and a chain rule. And this point where if I'm going quickly through problems, what I would actually do is I'd probably just highlight for myself, I'd do something like, think of that as a 4. Just as a kind of quick mental, I know how to do this. Okay, this is not difficult. It's not going to trip up my brain. If I see a 4 there, if I see a y there, it'll trip up my brain. So that's a quick way to check through.
So that would just be 2x cosine x plus 4.
No.
Okay.
No. Product rule. Okay, so this one we look at, we go, okay, it's a thing times a thing, so we need to product rule it. So it's going to be 2x times sine of x plus y plus x squared cosine x plus y, and we're done.
Yeah, times 1.
Times 1. times the hidden one that's sitting over there that we didn't see. Yeah. Okay. All right, and this bunny?
X squared plus y.
All right. Agreement?
Mm-hmm.
Sweet. Okay, moving on. All right, so notation. So this is actually the notation that I will use more often. So we want to differentiate. Did you see what I did there? We want to differentiate between full derivatives, which we've been doing a lot in. I'm sorry, I'm a mathematician. This is as good as the humor gets. We need to be able distinguish. Thank you. We need to be able to distinguish between the full derivatives we've been taking for functions of one variable and these weird-ass things where we're holding something constant and only taking the derivative in one dimension. So we use funny notation, because why wouldn't we? We use these little squiggly d's. So it's drawn like that. Okay, this is Leibniz's notation. And I think this is more common than the notation that the textbook has used that I've been using to now. So here you can see explicitly, so the point is that you read this and you go, aha, okay, this says take the derivative of z with respect to x, holding any other variables constant. Okay, and so it works not just for 2 variables, but as many as you want. You can use the similar notation here if you're wanting to be explicit about the name of the function. this notation over here that we've seen, and also you will sometimes see a big D. And it depends quite a lot on which country you're in and which discipline you're in. And sometimes within physics, different areas of physics use different conventions. Sorry. Okay. I will tend to use this because it is the most familiar, and it's kind of how I learned when I was in South Africa. Yeah.
I've also seen like it's almost written the same as what the 1 and the 2 down there, like
yeah.
in purple, but then instead of a 1 or a 2, it just has an X and a Y.
Oh yes, that's a good point. Yeah. So we're going to talk about that as well. The problem with that is it can get confusing. So we'll see that. So you might see. So I think what you're saying is we could write this as. Yeah. So you will actually see that. Yeah. Thank you. Okay. And we use the same notation if we want to evaluate at a point as we do with standard derivatives. So we use the line saying evaluate this at this point here. Okay. Exactly as you might expect. All right. So please evaluate the first derivative with respect to x and the first derivative with respect to y at the points of this function here. It should be pretty straightforward. So we know that f1 okay. So what does this number tell us?
When you change x and you hold y constant at 1,1 basically, right? Then z decreases by 2.
Exactly. So if we go back and look at our picture, which I think I put in here. Okay, so if you look at this picture here, if we're thinking, so we're holding we're holding y constant, and we're letting x change. So I think we're on this line here. Sorry, I'm just going to switch over here. It's going to be better to see. Okay, so here we just found a -2. What is that -2? Well, it said if we hold y constant and we look at how our function changes when we change x, it changes by -2. So that -2 is the slope of this line here, of our tangent line. So it should start to sort of meet up. And it shouldn't be a surprise then if we switch over to our y. We might expect when we hold x constant and we just look at the derivative of the slope at that point with respect to y, we should also get a -2. So let's go and just check it. Okay, if you take a derivative here and you plug in 1, 1, you'll get -2 again. So we are still finding, just like when you evaluated slopes in one dimension, you were finding the slope of a tangent line. You are finding the slopes of tangent lines here. Okay. So we can do more. So because we've got surfaces, we can go beyond this. And the idea is that we can find tangent planes and we can find normal lines. So if you imagine having a surface at any particular point, you can imagine that there's a tangent plane to it, and therefore since you've got a tangent plane, there must be a normal line, which is the normal to the plane, and therefore normal to the curve. So we want to think a little bit about that, with the usual proviso that we're assuming that we have a nice smooth curve, not something with a point where you couldn't find derivatives. So if you read through this, it all sounds a little bit hairy, but in fact, what we're going to do in order to find our normal vector, or our normal vector to the curve, is stuff that we've already seen before. So I'm sorry, I'm switching back again. What is this? So let me just take out this. Okay. So think about what we're wanting to do. We are wanting to find the tangent plane at that point. How do we find planes?
Normal vector and a point on the plane.
Right, a normal vector and a point on the plane. Okay, so we have the point on the plane, so if we can get the normal vector, we're good to go. Okay, how do we find normal vectors?
Take the cross product of two vectors in the plane.
Awesome. Okay, tell me about two vectors that we have in this.
Two tangents.
We have our two tangents, which is going to give us our two vectors. We're going to take the cross product, that will give us our normal, and then we've got our plane. How pretty is that? So this is why we had to do everything last week, because we really use it this week. So now, if we go back to what all this crazy stuff on here, come on, no. Okay. So this initially might have looked a little hairy, but all we're saying is, okay, well, if we take the tangent directive for our tangent vector, our T1, we can create a vector in the direction of that line, the one where we held y constant and let x vary. We can create this like so. And so you'll notice here what's happening here. It says I'm really changing 1 unit in the x direction, and I'm changing whatever my slope is units in my z direction, and I'm not changing at all in my y direction. Okay, so that makes sense. I do the same thing for T2, for my second tangent vector. This says if I change 1 unit in y, I will change this many units in k, and I'm not changing in x. So those are my two vectors that I can use that are tangent to my plane. I'm going to cross product them, like we learned, and here we go. Got a normal vector. So just remembered, someone pointed out I put a minus sign wrong in the I think when I split up last week, I split this up into 2 by 2s, and I think there was a minus sign wrong in the notes. Sorry. I'll change it. I mean, it is relevant if you're using the formula, but I'll make it sure it's correct in formula sheets. Okay, so we take the determinant, or however you choose to find the cross product, and this is what you get. Okay. So we've done a lot so far. Just to kind of clarify where we're at, we've got a surface. We look at what happens to the slope, to the tangent on that surface if we hold x constant. We look at what happens if we hold y constant, and that gives us two vectors. We cross product those, so now we end up with a vector that is pointing, well, either out or into our curve, but it's normal to the curve. And the final step that we want to do is use that to find our tangent plane, and we do that using what we did last week, which said if you have a normal and you have a point on the plane, you're good to go. So this is straight using stuff from last week. So we've got the equation of tangent plane to some surface at the point AB, f of AB. Is exactly what you would expect. This is what you've got if you went, if you think through the process that we did. We said the normal dotted with any point so we said the normal dotted with any vector on the plane has to be equal to 0. We've applied that over here. And we're good to go. Okay. Questions so far? So I think I will pretty much finish there, but I want you to see where we're going so that you know where we're headed next week. Yeah.
Okay, one question to the equation, the second one of z in green. Like what's happening here? So basically take my actual plane that's actually on my 3D surface plus the first derivative with respect to x, and then I multiply that by x minus a. Like why do I multiply it by x minus a?
Okay, so what you're wanting to think about is where that formula comes from. It comes from saying, okay, how do I find the equation for a plane? I need something that's normal to the plane, and I need a point on the plane.
So first thing is the point on the plane, and then the second two are the normals.
No. What I drew here is the dot product that you would use. So you would go back and use this normal and dot it the way you would to find a plane, and when you multiply out that equation, that dot product, you end up with the scalar product that's shown there. I will write out that derivation. Okay. Alright, I have 2 minutes. Where do we go from here? We talk about higher order derivatives, of course we do. And of course you can imagine now we have partial derivative with respect to x and partial derivative of y, and each of those things in their own right is a function of x and a function of y. So you can also take partial derivative of y of partial derivative of x and mixed partials and things like that. Okay, so we talk a little bit about that. And you can imagine going up to 3 dimensions, it's just silly. Okay, so you end up with things like mixed partials. Okay, but the nice thing, the good thing, is that it turns out that if you have nice curves, taking the derivative with respect to y first and then with respect to x is in fact the same as going a derivative with respect to x first and then with respect to y, if your curves are well behaved, which ours are. Okay, 1 minute. Alright, so we're going to talk about that. We're going to talk about the chain rule, because of course we are. But the key thing that we're going to do is take these ideas and pull this together into a new kind of derivative idea. We're going to define this thing called the gradient using our partial derivatives, which is a vector that tells us about the slope of, or the tangent of our surface. And we're going to use that to talk about the directional derivative. So what about if we want to find out the rate of change in not the x or the y direction, if we want to go in any direction given to us by a vector? So we pull this all together to then be able to go, okay, I want to know the rate of change in that direction. We can calculate it. Alright. Good job, everyone.